and then we'll make a few general announcements, and then we'll go ahead and begin. Okay, so it looks like the recording has now started. So first thing I wanted to mention was at this point, the exam 1 grades have been posted. You should have received a notification over the weekend about that grade going up. In addition to the grade going up, if you go into the exam folder, I think so that was week 4's kind of lab folder, there's exam 1 study material. You should be able to find the exam located there. You can find the exam document and the full written solution that I have for it in that folder. You should also be able to access it, I think, from your gradebook if you click on the assignment. So again, the exams have been graded. You should have your feedback. I'll be handing back the physical copies in lab this week. So you will get the physical copies back at that point. Otherwise, I wanted to remind you guys that there will be lab this week. It will be our 3rd lab, which will be focused on psychometric processes. So you do have to come to lab this week. The lab experiment is a little bit longer. So it's probably going to take almost the full time for all groups. So do attend at the beginning of lab. We'll rotate through taking data sets, kind of similar to what we did in lab 1. The thing about this lab is that we're going to try and do a heating and humidification and a cooling and dehumidification style setup. And we do have to change between the two. And it does take a little bit of time for the system to kind of reach a steady state. So there'll be some time in between our data sets where you'll have essentially time to work. So if you do want to bring some outside work for that time period, or if you want to use that time to kind of get started on your lab right up with your groups, you're welcome to do that. But again, it will take some time between our data measurements. So just assume that we're going to be in lab for almost the entire period this week. But if you want to bring something for part of that time, again, you will be welcome to do so. Okay. Otherwise, if there's no questions about lab, just a reminder, do bring your safety glasses to lab so that we're compliant with all of the lab stuff that we need to deal with for just essentially lab safety. Otherwise, make sure you watch the pre-lab video dealing with psychometrics, and we should be ready to go for lab this week. Okay. Otherwise, let's go ahead and push forward, and let's take a look at the last part of our psychometric process, and that was going to be adiabatic mixing. And so adiabatic mixing is going to represent 2 essentially psychometric flows coming together and coming together as a mixture, and will leave as one flow. So traditionally with adiabatic mixing, we have a lot of things to take care of. We have to take account of a lot of different processes. And so on this one, I'm going to do it a little bit backwards. I'm going to talk about what's going on mathematically first, then we'll take a look at what's going on for the psychometric chart. So in terms of our system, we're going to have 2 or more inflows, 1 outflow, and we'll assume right now we're just going to do 2 flows mixing. And in terms of the flows mixing, we're going to have to account for several things, including the mass flow rate of the dry air at both the inlet and the exit state, and so, or inlet states, I should say, and the exit state. And so we'll have mass flow of air 1, 2, and 3. But in addition, we now also have to consider what is the mass flow rate of the water vapor at each of these conditions. So we'll have m dot vapor 1, m dot vapor 2, and m dot vapor at state 3. Now, mixing tends to get a little bit more complex than some of the other ones just because of the nature of the setup. And so this is why I want to spend a little bit of time going through the mathematics, and then we'll see what comes out of the mathematics. So similar to our previous approaches, we're going to have 3 main equations. We're going to do conservation of mass in our 2 species, and then we're going to have our conservation of energy equation. So in terms of conservation of mass, we're going to focus on air first. And so in terms of air, we have the change in mass of the air inside of our system with respect to time. Our system is just going to be the region where it is mixing. And we're going to say this value, we're going to assume it's steady state. So we can say the left-hand side goes to 0. We're going to have the mass flow rate of the air coming in, which would be state 1, plus the mass flow rate of air at state 2. And then we have the mass flow rate of the air leaving. So dry air leaving at state 3. And if we go ahead and rearrange this, what we find is the mass flow rate of the dry air leaving has to equal the sum of the mass flow rate coming in for both of the individual inflows. And so while that may not seem that interesting, it'll be useful down the line. And so we'll just make note of that at this point. Now, if that was for the air side of things, let's go ahead and take a look at the water. And we'll also include that we have the vapor included in this water setup. So water and water vapor. And so if we do the setup, we have the change in the mass content of water inside the system. Said it's going to operate at steady state, so that's going to go to 0. And we said, well, we have to then account for all of the mass flow rates of vapor. So we have the mass flow rates of the vapor coming in at state 1 and state 2. And then we have the mass flow rate of the vapor at state 3 leaving the system. And so, like we did with the mass flow rate of the dry air, we can go ahead and solve for the mass flow rate of the vapor leaving by just summing up the two vapor inflows. And so 1 plus mass flow rate of vapor at 2. Now, these two are going to give us the ability to push forward. Now, what we're going to do is we want to go ahead and combine these two equations. Now, the way that we're going to go about combining them is recalling our definitions so we can get the mass flow rate of the vapor. This was the humidity ratio times the mass flow rate of the dry air. And so what we're going to do is we're going to do this for each component. Now, what's different about the other cases we had a single inflow, single outflow, so the mass flow rate of dry air was the same. Now we have to do this per case. So if we wanted to say this was I, this has to be I, and this has to be I. And so if we go ahead and use this to substitute into our water equation, what we're going to end up with is the mass flow rate of the dry air at state 3 times now the humidity ratio at state 3. This is going to equal the mass flow rate of dry air at state 1, humidity ratio of 1, plus the mass flow rate of dry air, humidity at state 2, humidity ratio of state 2. Okay. So that's our first step forward, but we're going to go ahead and make another substitution. That substitution is now going to be bringing the mass flow rate of dry air at state 3 in to this left-hand side. And so we know the mass flow rate of air at state 3 would be the mass flow rate of dry air at state 1 plus the mass flow rate of dry air at state 2. Now that's times the humidity ratio of 3. This is going to equal mass flow rate of air at state 1, humidity ratio 1, plus the mass flow rate of dry air at state 2, humidity ratio at 2. And so we can go ahead and separate these out. And so if we separated them out, we could say, well, we'd have the mass flow rate of dry air at state 1. This would be humidity ratio 3 minus humidity ratio of 1. This is going to equal mass flow rate of dry air at state 2, humidity ratio of 2 minus humidity ratio of 3. Now, if we rearrange this one more time, we can end up with a ratio. So if we have the ratio of the mass flow rate of dry air at state 1 over the mass flow rate of air at state 2, what we get is we get a ratio of the difference in these humidities. And so we'll have the humidity ratio at state 2 minus the humidity ratio at state 1 over the humidity ratio of state 3 minus the humidity ratio of state 1. Now, this is just the setup. Now we'll get to why this is important once we do the next part, and that is conservation of energy. And so again, this is just
W2 minus W3.
That was just part 1. Okay. Any questions on part 1?
I could be wrong, but did you maybe switch out a 1 for a 3 in the numerator? Shouldn't it be W2 minus W3?
Yeah, I think I did. Sorry. Good point. You're right. This is a 3. Could be 2 minus 3 over 3 minus 1. Yeah, I got ahead of myself on my nomenclature there. So yeah, so again, W3 here. My bad. Okay, thank you for catching that. All right, so let's go ahead and push forward now into conservation of energy. And so for conservation of energy, we're going to set up our energy accounting equation. So dE dt for the system, we're going to assume steady state, so that goes to 0. This is going to equal the heat transfer rate in minus the rate of work out, plus then we have the sum of the mass flow rates in times now the enthalpy in plus the kinetic energy plus the potential energy, end parenthesis, and then we have minus the sum of the mass flow rates out times the enthalpy plus the kinetic energy plus the potential energy. Okay. And so at this point, we have to apply some assumptions. Now, in our mixing chamber, we generally aren't going to have any work, so no turbo machinery, so we can get rid of that. No compressor, no pump, no turbine. We generally aren't going to be concerned about the change in potential or kinetic energy, so we can generally let those go away. And then the last one we will note is this is called adiabatic mixing. And so if it's adiabatic, that means we're doing it without heat transfer. And so we let Q dot go to 0. And so what we end up with is it's just going to be like our previous mixing chambers, our heat exchangers. It's all going to be dependent on the mass flow rate times the enthalpy. It's going to be the sum of all of those values. And so what we want to do is we want to go ahead and sum these up. And so we have to now keep track of all of our different flows in and out. And so in terms of our setup, we're going to have going into the system, we'll have the mass flow rate of the dry air at state 1. We'll multiply that by now the enthalpy of the air at state 1. We'll then add in the mass flow rate of the vapor at state 1, enthalpy of the vapor. We got enthalpy of the vapor at state 1. Then we'll do the mass flow rate of the dry air at state 2, enthalpy of the dry air at state 2, plus the mass flow rate of the vapor, state 2, enthalpy of the vapor at state 2. And then we have state 3, so minus the mass flow rate of dry air at state 3, enthalpy of the dry air at state 3, minus the mass flow rate of vapor at state 3, enthalpy of the vapor at state 3. And so those are going to represent our different flows in and out of the system. And so what we're going to do now is we're going to apply this equation down here again, our mass, converting our vapor into mass flow of dry air. And so again, we're just going to make that substitution here, and we're going to make that substitution here, and then we're going to make that substitution here. And so what we end up with is we have 0. This is equal now the mass flow rate of dry air at state 1 times the enthalpy of the dry air at state 1 plus the humidity ratio at state 1, H sub G at state 1, plus now the mass flow rate of the dry air state 2 times the enthalpy of the dry air at state 2 plus the humidity ratio at state 2 plus here multiplied by the enthalpy of the vapor at state 2, minus now the mass flow rate of the dry air at state 3, H of air at 3, plus the humidity ratio at 3, and the enthalpy of the vapor at state 3. Okay, so that is going to be the combination that we want. Now, if we remember, we can say, well, enthalpy of air plus humidity ratio times H sub G. We can combine this into the total enthalpy on the per unit mass of dry air basis. And so these kind of represented our truncated enthalpies. Remember, this would be kilojoule per kilogram of dry air. So again, dry air basis is all that we're doing. And so we're going to go ahead and use this combination. What we end up with is 0. This is equal to the mass flow rate of the dry air times the enthalpy at state 1 plus the mass, and that'd be at state 1 for the mass flow rate, plus the mass flow rate of dry air at state 2, enthalpy of 2, minus the mass flow rate of dry air at state 3 times H sub G 3. Now, what we can do is we can say, well, mass flow rate of 3, we know that this is the mass flow rate of air at state 1 plus the mass flow rate of air at state 2. And so we can make that substitution. We can go ahead and then rearrange this one more time. So I'm going to do that in one step. And what we'll end up with is we'll have the mass flow rate of dry air at 1. And so we'll reduce the number of variables. Instead of having 3 mass flow rates, we'll now relate it down to 2. And so we'll be able to combine our enthalpies to H1 minus H3 for air at state 1. Plus then we'll have the mass flow rate of dry air at state 2. And at state 2, we then have H2 minus H3. Now, what we can do is rewrite this one more time, and we'll see that we have a mass flow rate of air at state 1 divided by the mass flow rate of air at state 2. Well, this is going to equal, and if we've done this correctly, we should get H2 minus H3 divided by H1 minus H3 minus H1. This is also going to equal, if we combine this, W2 minus W3 over W3 minus W1. And so we now see that there's this intertwining of the change in the humidity ratios and our changes in the enthalpies. And that's all going to be related to this mass ratio over here. And so what this means is that when we go to the psychometric chart, we're going to see some things fall out. So this is kind of the important takeaway, I guess, from this mathematics. Now, if we go to the psychometric chart, which we're going to do here on the next slide, we have this mixing process, and we're going to have two states. And so if we set, we'll set state 1 to be right here. And let's set state 2 to be right here. So we have two different inflow conditions. Well, if we go ahead and block off what the humidity ratios are, should be W1. This value over here would be W2. And then if we wanted to, we can block off our enthalpies. So this would be H1. And we go up here, we have H2. Now, what that previous equation was telling us was that if we set this up correctly, which we did, that state 3 is going to lie somewhere on a line between state 1 and state 2 in the psychometric chart. So if we just draw a straight line between these 2 points, we've established all possible areas where state 3 can lie. Now, how far between state 1 and state 2 the actual point comes down to relates to the individual mass flow rates for each of those states. So if state 2 was larger, it will be closer to state 2. If state 1 is larger, it will be closer to state 1. And so we can choose whatever state point 3 is based on just changing the mass flow rates. And so if we kind of think of it in terms of like a linear interpolation setup, basically we now have these two axes that we have, and we can basically kind of move between the states using now enthalpy and the humidity ratio. And so the enthalpy and humidity ratio are going to be very important for helping us determine state 3 when we do our actual application, we do the actual calculations. So we're going to need the humidity ratio, we're going to need enthalpy to determine state point number 3. And so this is the process that we're going to have to use to now establish state 3. Okay, so the short answer on this is we're going to see a slightly different approach now when we do all of the homework style problems on adiabatic mixing. Okay, so now that we've seen what we'd expect on the psychometric chart, let's go ahead and work an example problem. And so we'll go ahead and just save that. And we'll go ahead and switch to the example problem at this point. And I'm going to have to quickly switch back to this. Hold on. I don't have the pen marker here. Okay, there we go. Should give me the ability to write on it now. Okay. So we have this example problem where we're going to work. We're going to actually apply all of these concepts, and we're going to see how everything comes together for these psychometric processes. So in this problem, what we're going to be doing is we're going to have two air streams that are going to be mixed in a steady and adiabatic fashion. The first stream is going to come in at 35 degrees Celsius, 30% relative humidity, and have a flow rate of 15 meters cubed per minute. Well, the second stream is going to come in at 12 degrees Celsius, 90% relative humidity, and a flow rate of 25 meter cubed per minute. We're assuming that the entire process happens at 1 atmosphere. We're asked to determine what is the specific humidity, the relative humidity, the wet bulb or the dry bulb temperature, and the flow rate of the mixture at state point 3. And so there's a lot that has to happen in this problem. So let's go ahead and begin by writing down all of our known parameters. And in terms of our known parameters, we have two states to establish. So the first state that we have to establish is the first one. So state number 1, and we know that the temperature is going to be 35 degrees Celsius. We are going to know that we have a relative humidity of 30%. And we also are going to know that we have a volumetric flow rate for number 1 of 25 meters cubed per minute. Okay. So that's state number 1. For state number 2, we also have the incoming temperature. This is going to be 12 degrees Celsius. We'll have the relative humidity at state 2. This is equal to 90%. And then the last thing that we have is the volumetric flow rate at state 2. This is equal to 25 meters cubed per minute. So those are our knowns. The last thing that we're going to note is that we have the pressure, P1, P2, and P3. These are all going to equal 1 atmosphere. And for conversion purposes, this is 101.325 kilopascal. And so we have the pressure of the system. Sorry. All right, so once we have all of those properties that we know, we should go ahead and write what we need to find. And so in terms of our find statement, we asked to find what is first the humidity ratio at state 3. We're asked to find what is the relative humidity at state 3, what is the actual temperature of state 3, and then lastly, what is the volumetric flow rate at state 3. So we have a lot of things that we're going to be looking for in this problem.
Professor?
Yes.
Volumetric flow rate for the first one is only 15 meters per second.
Yeah, sorry. Thank you. I looked at state 2 and I wrote state 1. So thank you for pointing that out. All right. Okay. So now that we have everything set up, let's go ahead and get to what we need to assume to move from state 1 or to find what we need move from our knowns to our find statements. So let's write down what do we need. Now, in terms of the assumptions, we're going to assume it's going to be an open system. So we're going to use the rate form of the energy and mass balances. We're going to need enthalpies. We can assume that it's going to be a steady state process. We're going to assume that it occurs in an adiabatic fashion. And we can assume that we're going to deal with air as an ideal gas. And the mixture can be treated as an ideal mixture. We're also going to neglect our kinetic and potential energies because we don't expect those to play much of a role in this energy balance. And so that should give us a pretty good starting point in terms of all of the assumptions that we need to make. So let's go ahead and push forward into the analysis. Okay, so for the analysis, what I'm going to suggest for this case, because we have a lot of things going on and there's a few things that we need to kind of figure out here at the beginning, is let's go ahead and look at each state independently before we do any sort of mass or energy balance. So let's just go ahead and take a look at what's going on at state number 1. Now at state number 1, just to recap, we know that the pressure is going to be 101.325 kilopascal. So we're going to use that for our calculations. Now, in terms of the first thing that we need for a calculation, we know that we're going to need the temperature that's going to come into play. We know that that was 35 degrees Celsius. And so we have that variable, and then we also have the relative humidity. This was 30%. Now, relative humidity, we can say, well, we know that will get us the partial pressure of the vapor at state 1 if we know the saturation pressure at state number 1. And so we said, well, to get saturation pressure, we're going to have to use the temperature at state number 1. And the temperature, when we go to the tables, we said, well, that's just the saturation pressure. So we can get P sub G1 at this point. And so that value is going to be 5.6291 kilopascal. And so then we're going to say, okay, we can look up P sub G1. We can get P sub vapor now because we know the relative humidity. Now, while we were in the tables, we were also going to go ahead and realize we need to do an energy balance. So we're going to need the enthalpy of the vapor. So we'll look that up, and that is going to be 2,564.6 kilojoules per kilogram of vapor. And so those are going to be the first lookup parameters that we have. Okay, so now that we have that, we'll realize we can go ahead and solve for the vapor pressure. If we now know the vapor pressure, the key parameter that we always want for our balances, we said, was the humidity ratio, the specific humidity. Now the specific humidity we said was going to be equal to 0.622 times P of the vapor at state 1, the partial pressure, over the total pressure minus the partial pressure of the vapor. Now, if we said we could use the saturation pressure and the relative humidity to solve for that, we could also substitute that into our equation. And so we could just rewrite this one more time as the 0.622 relative humidity at state 1 times now the saturation pressure at state 1 over the total pressure of state 1 minus the relative humidity at state 1 times P saturation at state 1. And so again, that was just combining our relative humidity with our specific humidity. And if we go ahead and do that calculation, our humidity ratio or specific humidity is equal to 0.01052. And this would be a kilogram of vapor per kilogram of dry air. And so we have the specific humidity at state 1. Okay, so now that we have that, we want to go ahead and try and deal with something else. And that was, what is our flow rate? And so the last thing that we did know was that our volumetric flow rate at state 1, this is 15 kilograms per minute. And we need to now get this into a mass flow rate. And so if we recall, we could say a mass flow rate. This would first be our volumetric flow rate divided by our specific volume at state point 1. Okay, so we need to figure out what is the specific volume. Now, at this point, what we're going to do, yeah, sorry, I'm not doing well today with my unit stuff. Yeah, it'd be meters cubed per minute. We're looking for kilograms per minute is what we're looking for here. So what we need is we need to get our specific volume here at state 1, but we have a mixture. And so it gets a little bit more complex, but what we're going to note is that our humidity ratio is still a pretty small number. So if we wanted to think about this, that means that we have a very low amount of water per unit mass of dry air. It's mostly just air. So what we're going to do is we're going to say, well, let's go ahead and consider the case where we just have basically air by itself. And so if we do that, we can say the specific or the relative, not relative, we can say that the specific volume that we have for state number 1 will just be of the air. So we can take RT divided by the partial pressure of the air at state 1. They said, well, if we wanted to expand this is going to be R of the air times T, and we could make that same trick that we did up here. So this would be P1 minus P, we'll do P vapor here first. So this would be P vapor 1. I don't know why it's not letting me, oh, there we go. That will let me erase. Over R times T1 over now P1 minus V1 PG1. Okay, so all we have to know now is the gas constant for air. For air, that this value is 0.287 kilojoule per kilogram Kelvin. We've looked up everything else, and so at this point we can go ahead and calculate our specific volume for state 1. This is 0.8876, and the units are going to be a meter cubed per kilogram. And so once we know that, we can go ahead and bring that over here. We can say, well, we can calculate the mass flow rate now because we know the volumetric flow rate, and we'll note that this would be now the mass flow rate of the dry air at state 1. So this would be now the volumetric flow rate divided by the specific volume of state 1. And so if we do that, what we get is we have 16.6 units are going to be a kilogram per minute. And so we have our first mass flow rate. It took a little bit, but we got to this point. Okay, so if that is the first thing that we needed to do, let's go ahead and now push forward into the second part, which is the state 2 setup. So basically, we're just going to repeat this now for state 2. And so just to kind of keep this a little bit shorter, what we know at state 2 is the temperature is 12 degrees Celsius. So if we wanted to do our lookup parameters, we know that we're going to need P sub G2. And the pressure for the saturation condition is going to equal 1.4191 and this will be a kilopascal. We also are going to need to look up the enthalpy for the vapor at state 2. And so it's going to be 2472.48. And the unit's going to be a kilojoule per kilogram of vapor. Okay, so once we have that, the other part that we know, we have a relative humidity of state 2. It's going to be 90%. And so if we recall, this would give us the partial pressure of the vapor over the saturation pressure at state number 2. And so with all of this information, we can say, well, at this point, we want to repeat the previous calculation from part 1. We want to get the specific humidity ratio. So we do 0.622. And I'm going to go ahead and just get to the final form. So Phi2 P sub G2 over the pressure at 2 minus Phi2 P sub G2. And so we have it now as a function of the relative humidity and the pressure of the saturation point at state 2. So again, this is all a function of just T2. And so at this point, we know everything that we need, and so we can go ahead and calculate the humidity ratio at 0.2. This is going to be 0.00794 kilogram of vapor per kilogram of dry air. And so we now have the two humidity ratios that we need coming in. Now, one thing I do want to point out is even though state 2 has a higher relative humidity, it has a lower humidity ratio than state 0.1 because of the temperature dependence of that process. So remember, even though you have a higher relative humidity, doesn't mean anything in terms of your actual humidity ratio, because that is, of course, the function going to be more of a function of temperature. So I just wanted to point that out in this case. Okay, so the last thing that we have for state 2 was the volumetric flow rate. This was going to be 25 meters cubed per minute. And so 25 meters cubed per minute, we need to convert this into a mass flow rate. We said this is going to give us the mass flow rate of dry air at state 2. And so we're going to repeat what we did up in state 1. We're going to have the specific, specific volume here at state 2. This is going to just be using the ideal gas law at state 2. And so this will be P of the air at 2. And so we can, again, go ahead and expand this T2 over P2 minus P2 P sub G2. And so if we go ahead and make this calculation, we have the specific volume at state 2, 0.81799 units are going to be a meter cubed per kilogram. And so if we bring this all together, what we can do is now go ahead and calculate what is the mass flow rate of the dry air at state 2. And this value ends up being 30.56. Units are going to be a kilogram per minute. And so we'll leave it in that form. Okay, so now we've spent some time. We've figured out how to apply all of these parts. We've gotten state 1 and state 2. Now comes the complicated part of finding state point number 3. And so to find state point number 3, we're going to have to use our energy and mass balances to figure out everything that we need to know. And so to get to state 3, that's exactly what we're going to do. Now, the first thing that we should do is go ahead and look at our mass balances, and we'll start with air. In terms of air, we have the change in mass of air with respect to time inside of the system goes to 0 because of steady state. Then we have the mass flow rate of the dry air at state 1 plus the mass flow rate of dry air at state 2 minus the mass flow rate of the dry air leaving at state 3. We have now the mass flow rate of dry air at state 3 equaling the mass flow rate of dry air at state 1 plus the mass flow rate of dry air at state 2. So we saw that from our previous example. Now what we could do in this case is we can go ahead and calculate the mass flow rate of dry air at state 3. If we wanted to do that, we can just know the two previous values, and we can say that this becomes 47.49 units on this would be a kilogram per minute. So we have the mass flow rate of the two flows combined for air. Now, if we repeat this on the water and water vapor side, we can see that we should end up with something similar. So change in the mass of the water inside the system with respect to time goes to 0, and we'll have the mass flow rate of the vapor at state 1 plus the mass flow rate of the vapor at state 2 minus now the mass flow rate of the vapor at state 3 leaving. We can now change this around, solve for the mass flow rate of the vapor at state 3. This will equal the mass flow rate of the vapor at state 1 plus the mass flow rate of the vapor at state 2. Using the substitution that we've used, the mass flow rate of the vapor can be the humidity ratio times the mass flow rate of dry air. we can get that we have the humidity ratio of 3, mass flow rate of air at 3 equals the mass flow rate of air at 1, humidity ratio 1, plus the mass flow rate of air at state 2, humidity ratio of 2. And so what we want to do is we said we want to first solve for what's the humidity ratio at state 3. So doing that, we can get the humidity ratio of state 3. This is the mass flow rate of dry air at state 1, humidity ratio of 1, plus the mass flow rate of dry air at state 2, humidity ratio of 2, divided by the mass flow rate of dry air at state 3, which we know is just air of 1 plus air of 2, which we calculated. And so using all of this, we can say, well, at this point, we can now calculate what is the humidity ratio at state 3, because we know all of the humidity ratios at state 1 and state 2. We know the mass flow rate at 1, 2, and 3 for dry air. And at this point, we'll put all of those numbers in our calculator, and we get the humidity ratio is 0.00887 kilograms of vapor per kilogram of dry air. And so there we go. We have our first deliverable taken care of. Okay. So that wasn't too bad. We just used conservation of mass. We got one of the things that we needed to take care of off the list. And so now we just have to figure out what is the relative humidity and the temperature at state 3. So let's go ahead and do that. We realize temperature is going to involve some sort of energy state. So let's go ahead and look at what happens when we apply conservation of energy for the system. And so in terms of the conservation of energy equation, change in energy inside the system, this is equal to the heat transfer rate in minus the rate of work out, plus then the sum of the mass flow rates in times the enthalpy plus the kinetic energy plus the potential energy of the flows in minus the sum of the mass flow rates out. Then we have the enthalpy plus the kinetic energy plus the potential energy of the flow leaving. Okay. So we can go ahead and apply assumptions. So left-hand side goes away, steady state. Heat transfer rate also goes to 0 because we said it's adiabatic. We have no turbo machinery in the system, so we can get rid of the power. We said that we could assume that there was no kinetic or potential energy effect, so that goes away. We're left with mass flow rates times enthalpy, and that's exactly what we kind of expected at this point. Now, what we'll do is we'll go ahead and step by step work through all of the details. And so in terms of the mass flow rates coming in, we'll have the mass flow rate of the dry air at state 1 times the enthalpy of the air at 1 plus the mass flow rate of the vapor at state 1, enthalpy of the vapor at state 1. We can now repeat this for state 2, so the mass flow rate of the air at state 2, enthalpy of the air at state 2, oops, it should be air state 2. Then we have the mass flow rate of the vapor at state 2, enthalpy of the vapor at state 2, minus the mass flow rate of the dry air at state 3, enthalpy of the air at state 3, minus the mass flow rate of the vapor state 3, enthalpy of the vapor at state 3. So a lot of things to keep track of, but again, we just had two basically flows at each of our states that we've established. We put those onto paper, and then we can go ahead and combine into a single flow the enthalpies. And so again, this is going to be just the humidity ratio times the mass flow rate of dry air. We're going to make that substitution everywhere we see the mass flow rate of the vapor. And so what we'll end up with is the mass flow rate of dry air. We'll have enthalpy of the dry air at state 1 plus now the humidity ratio of 1 H sub G1 plus then the mass flow rate of the air at 2, the enthalpy of the dry air at 2 plus the humidity ratio of 2 H sub G at 2 minus the mass flow rate of the air at state 3, enthalpy of the air at state 3 plus the humidity ratio of 3 H sub G 3. And so we've gone ahead and made this combination, and we'll note that this combined value again gives us the kind of total enthalpy on a per unit mass of dry air. So we have H1, H2, and H3. Again, per unit mass of dry air. We'll make a note of that. So H1, this would be C sub P times T1 plus humidity ratio 1 H sub G1. Units on this would be a kilojoule per kilogram of dry air. So again, dry air basis for this setup. Now, what this allows us to do is reset our energy equation into 0, equaling the mass flow rate at state 1, enthalpy of state 1, plus mass flow rate 2, enthalpy of state 2, and then minus the mass flow rate of state 3, enthalpy of state 3. And so we've just reset this equation. And so what we want to do is we want to solve now for the only unknown, which would be enthalpy of state 3. So we have the mass flow rate, this would be dry air, this would be air, and this would also be air at state 3. So we have the mass flow rate of air at state 1, enthalpy 1, plus mass flow rate of the air at state 2, enthalpy state 2, divided now by the mass flow rate of dry air at state 3. And so if we go ahead and do the combined lookups, so again, enthalpy 1 using C sub P T, T will be in degrees Celsius. And we say C sub P, I'll go ahead and write this down. For air, this would be 1.005 kilojoule per kilogram Kelvin. So if we do those values, what we'll find is the enthalpy of state 1 will be 62.21 kilojoule per kilogram of dry air. We can get enthalpy of state 2. This is going to equal 31.69 kilojoule per kilogram of dry air. And then if we do this, put on these numbers, we can now solve for the enthalpy of state 3. Enthalpy of state 3 is going to equal 42.6 kilojoule per kilogram of dry air. Okay, so we now have a humidity ratio, we have an enthalpy, we have two parameters we can use to determine our state. So we now know W3, again, this was equal to 0.00887 kilogram per kilogram. We know H3, this was equal to 42.6 kilojoule per kilogram. And so what we want to do is we want to take these two variables, we want to convert that into our relative humidity at state 3 and our temperature at state 3. Now to do that, it becomes an iterative process because while we have the enthalpy, we could say enthalpy 3, this becomes C sub P T3 plus humidity ratio of 3 H sub G3. But this is a function, this is just temperature. This is a function of temperature, and that becomes a little bit harder. And we could set this up in Excel. We could do some iterative solving, but it would be easier to just take this to the psychrometric chart and use it at this point. And so knowing we have a humidity ratio, knowing we have an enthalpy, we can come down to the psychrometric chart. And I went ahead and added some lines. And so we know the humidity ratio at 3, again, 0.0088. I think that was 887. And so that's almost 0.009. So that's right here on the chart. So just a little bit shy of that, we draw a horizontal line. We see over here, we knew the enthalpy at state 3, which is equal to 42.6. So this would be 40, 41, 42, and just over halfway between those two lines. We draw another line coming down. We see that those intersect right here. And so we'll call this point right here state 3. And so if we want the temperature, we just have to now move vertically here. And so if we come down here, we can say, well, that's 20. Let's say that's about 20.2. So T 3. This should equal about 20.2 degrees Celsius. We want the relative humidity. We can see that the closest line right here is about 60%. We're just below that. So if we wanted to estimate that value, well, we'll say that this value, we'll say it's about 59% in terms of that value. So there we go, 2 values calculated directly using the psychometric chart. Okay, now there's one more deliverable that we had left, and that was to calculate the volumetric flow rate for state 3. So volumetric flow rate at state 3. So what we want to do is we said, well, let's get the mass flow rate of dry air at state 3. Now we could do the specific volume at state 3. And so we could, again, calculate specific volume using the same method that we've done before. But what I want to show you is we could also do this with the psychometric chart. So on the psychometric chart, we have some lines that move up and to the right. So here's one right here. Here's one right here. And so we look for the closest one, and we see that this value is going to be 0.84. So that should be 0.85, 0.86. And we say, well, if we drew a line between those, we're maybe part way through, so not quite half. So maybe we say we're about 0.842, so not quite halfway, so not 2.5, just under that, so 842. And so we could say, well, this could also equal 0.842 meters cubed per kilogram. And so that's actually what it comes out to be, pretty close when we do the actual calculation, which means that if we finish this off, volumetric flow rate at state 3, so equal 39.96. This will be meters cubed per minute, which we can basically say at this point is probably going to be about 40 meters cubed per minute if we ignore some of our rounding. And so that is going to be the last portion of the deliverable. So we can go ahead and box that value. And then we had those 2 other values that we pulled right off the psychometric chart, about 20.1.2 degrees Celsius and about 59% relative humidity. So that is how we're going to be able to use the psychometric chart for some of our mixing processes. You will have to do something similar on some of your homework, so you will use the psychometric chart. It will be easier than doing the iterative solutions, which is why I wanted to do this example problem. But at this point, that is going to be the end of this example and end of the lecture today. So if you do have any questions about this, please let me know. Otherwise, just a reminder, we do have lab this week, so I will be seeing you either tomorrow or on Wednesday in your lab section. Remember to bring your safety glasses and try and watch the pre-lab video ahead of time. All right, otherwise, that is the end of class, and I will see you in lab this week.